All right, so we get to the last talk of this afternoon. Laszlo flew in from Canada last night. That should be saying he does live down the road and loses at football a lot of times. Using designs for crossing numbers.
So I would like to thank for the invitation to the organizers. I originally wanted to give a short introduction on crossing numbers and then explaining a proof that I believe is cute and solves a problem. But as this is so late, so maybe the introduction into crossing numbers will be longer and anyone can look up the details of the proof, but I will get somewhere in the proof. So this paper has a good number of co-authors. It started in an mathematical communities, mathematical research communities workshop of the American Mathematical Society. This is why we have so many on it. That's a program that I advise to everybody who is within 2 years from the PhD and not later than 5. There are all kinds of topics. There could be one which is relevant for you, and you don't have to look for a topic where you already do research, look for something nearby. So I recommend this experience to everybody. So what is a crossing number? Everybody knows what is a planar graph. You want to place the vertices on the plane and represent the edges with non-crossing curves that connect the points that correspond to the vertices of the graph. But not necessarily every graph is planar, and we still have to draw graphs which are not planar. So what is a graph drawing? So we map the vertices of the graph to points of the plane injectively. We map edges to simple curves that connect their respective endpoints. Curves are not supposed to pass through any other vertex. The crossing number of a drawing of a graph is the number of common internal points for all pairs of edges. And then finally, the crossing number of the graph is the minimum crossing number of over all of its drawings. So geometrically, there are infinitely many drawings. So that's a complicated problem. So this problem exists since the 1940s when Paul Turan was in a forced labor camp, which was a brick factory. And the brick factory contained certain kilns where the bricks were made and some open storage yards where the bricks were connected. And the kilns were connected by rail to the storage yards. And the trouble was that these rail tracks crossed, and at those points the bricks tended to fall down from the little trolleys. And then Turan started to think that how this should be designed in an ideal world so that the number of crossings is minimized. So this is Turan's remembrance to his problem in 1977. So Zarankiewicz made the conjecture for complete bipartite graphs that would correspond to n kilns and m storage areas. Every kiln is connected to every storage area, and we want to place them in the plane and connect them with continuous arcs so that we minimize the total number of crossings. So actually these drawings get something for free, namely that these curves are straight line segments. And the idea is that we put on the x-axis the kilns as evenly as possible. So the number of those in positive location differ by at most 1, the number of those in negative locations, and with the storage area similarly on the y-axis, and then connect them by straight line segments. So if you are willing to do a little algebra, you can work out the number of z and m. This is the number of crossings in this drawing. So believe me that this formula is correct. So Zarankiewicz conjecture used to be a theorem. since Carankiewicz published it. And then independently Urbanik published it with a slightly different solution. And it was republished in a book which was so popular that was even translated to Hungarian. And as a student, I amazedly saw the translator's comment, "This theorem is not true." But he dutifully translated the proof since he was paid for it, so it was only a footnote. Then graduate students pay attention. Two graduate students, Ringel and Kainen, independently started to ask questions about this proof. And still nobody has answered these questions. And Guy actually wrote an article with the title "The Rise and Fall of the Carankiewicz Theorem," which is conjecture again, and it needed some cleanup since it had references and applications, of course, like every theorem has. And this whole topic turned relevant in the 1980s since computer scientists started study crossing number questions, since it has relations to VLSI design, which is basically chip design, which was a big business. And when it was studied seriously and more than recreational mathematics, it turned out that there are actually different definitions of the crossing number. What I mentioned is the kind of the standard crossing number. But many papers that were actually published used different definitions. And then the natural question arose whether those definitions are all equivalent or not. And the answer is, who knows? So Park and Toth wrote a paper with the title "Which Crossing Number Is It Anyway?", where they wanted to separate these crossing numbers. And even that paper had a precursor. Boyan Mohar gave a conference talk in Vermont where he pointed out that there are inconsistencies with the definitions of crossing numbers, and somebody have to try to put it in order. So there is one thing which is relevant to mention here. Lakatos has a famous book, Proofs and Refutations, which applies Popperian epistemology to mathematics. And he had two basic examples that he discussed. One was Euler's polyhedral formula, and the other was the concept of a real function. So these were things where people thought about something and always run into some kind of contradictions, antinomies, these kind of things, and they had to clean up the definitions. And the way of cleaning up the definitions is do it in a way so that we keep our theorems. And these crossing number troubles are closely related to Euler's polyhedral formula, which is very intuitive, but if you think about it rigorously, it's extremely complicated. So this is some source of the problems. So I would like to speak about the Guy-Hill conjecture. So Hill was an architect who became interested in crossing numbers, and his question was how to draw the complete number with the minimal number of crossings. And that's the formula, which is known maybe up to 12 or 13 vertices, and otherwise it is still a conjecture. And the strange thing is that this number of crossings can be created in entirely different ways, and I will show some of those. So there is a lower bound for the crossing number of Kn, which is roughly 99% of this number, which should be enough for an engineer, but not enough for a mathematician. And there are some very narrow classes of drawings for which the conjecture is actually proved, but that's kind of a hope. So, the slope drawing. So consider here a K5 or a Kn in a way that the vertices are the vertices of a regular n-gon. and rotate it into a general position. General position means that no line segment that you see is horizontal or vertical. It should be easy. Then make a drawing of this in the following way. Instead of the plane, I make the drawing on the sphere. These kind of things are easily seen to be equivalent. So I consider separately the line segments that have positive slopes and the line segments that have negative slopes. And one will go on an upper hemisphere and the other will go to a lower hemisphere. And you have the crossings that you see, for example, this one and only one in this way. And actually the number in this drawing is exactly the number that I show you in the conjecture. So this drawing has an interesting feature, namely, if you draw it, you have a single cycle, this one on the boundary, that contains all vertices and nothing crosses it. So you can add this cycle there. So the other drawing would be the Sübchen drawing. I saw it for an even number of vertices, on 10 say. You know how a Sübchen looks like, that's it. So on the top and on the bottom of the Sübchen, I put a regular angon and put a straight line drawing of the angon there. This is why you see pentagons there. And then I connect the lower angon and the upper angon with geodesics, so with the shortest curves that curve them on the outside of the Sübchen. And that thing exactly has the same number of crossings as the other one, and it's different. Here you would not find a curve that goes through all points and nothing crosses that curve. So that's a different drawing. So there is another interesting thing to mention about crossing numbers, and that's the crossing lemma. That was discovered in the 1980s, oh, it's not shown, by two groups. One was Layton, and the other is Ajtai, Schwatal, and Szemerédi. So if we have a simple graph on n vertices and m edges, then either m is small, say we can have it without crossing, it can be a planar graph. But in this case, m is at most 4n, say, we are generous, or the number of crossings is bigger than m cubed over, say, 64 times n squared. So actually this lemma was conjectured by Erdős and Guy 10 years earlier, but those who proved it independently did not even know about that conjecture. So it's worth mentioning about Layton that he brought crossing numbers into VLSI. He made his PhD at MIT. He published his thesis as a book when he wrote it. Then he became a faculty at MIT, and currently he is estimated to worth $300 million. He is the owner of Akamai, the internet security company. So sometimes you see Akamai.com when you do a certain secure transaction. That's the same Layton. So this essentially comes from Euler's formula that the crossing number of a graph with m edges and n vertices at least m minus 3 plus 6. So why is this? Since if m minus 3n plus 6 is at least 1, then your graph cannot be planar. So it must have a crossing. But then remove an edge with a crossing and do induction and repeat this kind of argument. And with some kind of bootstrapping of this second formula, you can get the crossing lemma. So this is the point where I'm getting closer to the topic of the talk, K-planar crossing number. So basically the problem is the following. Instead of the crossing number of the graph, I want to ask the following question. Partition the graph into K graphs and draw that k graphs each in a different plane such that the sum of crossing numbers is minimal. You clearly save something compared to drawing on one plane. So the question is how much you save. What is the multiplicative factor that you can save? So this biplanar, this is the k equal 2 case, was raised by Owens in 1974 in an IEEE journal, and then there was some follow-up in the literature. It's worth mentioning that the thickness of a graph, another well-known parameter, is the minimum k such that the k-planar crossing number of the graph is 0. So we want to partition the graph into the minimum number of planar graphs. So actually Owens was interested in the biplanar crossing number of kn, the complete graph on n vertices, and he had a horrible result. It's at most 7n to the 4 over 1536 and a cubic term. And there was an improvement on this result recently by Durocher, Gaitner and Mondal, but they only improved on the cubic term, not on the leading term. So it looks like that leading term could be the truth. And now there is some numerology. What is the meaning of this 7 over 1536? This is a product of two fractions, 7 over 24 and 1 over 64. 1 over 64 is the leading term in the Hill-Harary conjecture. So the crossing number of the complete graph is supposed to be around n to the 4 over 64. So it looks like that for the complete graph, this drawing makes a saving factor of 7 over 24. Can we do this for all graphs? Well, we don't, but we can do something. Some more comments. If you ask if a graph is planar, then this is easily solvable in polynomial time. But if you ask if a graph is biplanar, if we can draw it on two planes without a crossing, then this is an NP-complete problem. So these k-planar drawing problems turn hard. So for k-planar, in particular to biplanar crossing number, I had a theorem with Eva and two Slovakian friends. We call this the 3/8 theorem. That says that if you can use two planes, you can make a drawing with 3/8 of the original crossing number. And this is done by a randomized algorithm that you will essentially see. And you can ask what is alpha k, or in particular alpha 2, which is the best saving factor that you can get for any graphs. What is such a smallest c? So for alpha 2 is less or equal than 3 over 8 because of this result. And perhaps the Owens drawing suggests that alpha 2 could be equal to 7 over 24, but who knows? So proof to the 3 over 8 theorem, which is essentially the same thing that I will do in a more generalized setting. So consider, it's not the right thing that I'm doing. So consider a random bipartition of the vertex set of the graph G. So toss a fair coin for every vertex and decide if you put it to U or W. And consider now an optimal drawing of the graph in one plane. So you have a crossing of two edges, and the 4 endpoints of the two edges fall into these U's and W's. So we have these 6 logical cases. that the endpoints of the crossing edges could be UU endpoints. A simple calculation gives that the probability of this situation is 1 over 16, that's an other 1 over 16, and you can consider all these cases. And imagine this in this way, that this is U, this is W. Say in U we assign 0 to the vertices, in W we assign 1 to the vertices, and then you can assign a weight to the edge, the sum of the weights of the two endpoints. It could be 0 plus 0 and 0 for a UU edge, a 1 plus 1 equals 0 for a WW edge, but for a UW edge it will be U plus 1 equal 1. So edges within are kind of similar numerically with this calculation, and edges across are different. And this is the idea for partitioning this graph for a drawing on two planes. So essentially the idea is that the best drawing that I had on one plane is a black box. I really know nothing about it. So I just try to mimic it with minimal changes when I make the biplanar drawing. Namely, I do the following. In the first plane, I put those edges which are spanned by U or spanned by W, so UU edges and WW edges as they were drawn originally, and in the second plane I put the UW edges as they were drawn originally. And now there is one trick that I can do. Since in the first plane I have UU edges and WW edges, and they may cross each other, there is nothing against that. But actually, I can move them apart. Since all UU edges are within some kind of ball, this is a compact set, so I have to translate that ball sufficiently far with a translation literally. So the UU edges are drawn as they were, just they are translated to far enough. In the second plane, you have the UW type crossings, the probability of such a crossing being shown in 1 over 4, so this is the expectation of those number of crossings, since every crossing of the original drawing D comes into play, and in the other plane, I have 1 over 8 for the probability of crossings of UU and UU edges. This gives a 1 over 8 times the crossing number of the expectation, the same term for the other. I add up these two.
You have 1 over 16, when you end up, you get 1 8.
Oh, that should be. Oh, 1 over 16 plus 1 over 16 is 1 over 8. I overlooked something. So that's the proof. And a couple of years ago, I met János Pach, Csaba Tóth, and Géza Tóth and thought about this problem. And we figured out that this can be generalized for any k, basically. And we proved the following theorem, that alpha k is between 1 over k squared and 2k minus 1 over k cubed, which is roughly a factor of 2 between the lower bound and the upper bound for alpha k. But we could not get very far from this. And for k equal 2, the upper bound still gives back the 3 over 8. We still don't know anything better than the 3 over 8 for 2, which seems to be the simplest question. And we pose then the question whether k squared times alpha k has a limit as k goes to infinity. This theorem says nothing about it. So I show what did I do with Pach, Tóth, and Tóth. Now we partitioned the vertices randomly, not into 2 clumps, but K-clumps if we want to draw on a K-plane, on K-planes. So this is what we did for an odd K, this is what we did for an even K. So K is 4 there, K is 5 here, 5 tuples, the vertices are in, and then the colors indicate what goes on one plane. So the yellow edges which connect this clump with that clump, or this clump with that clump, or is within this clump, will go on one plane. But basically that part can be pulled apart sufficiently far so that yellow edges here no longer intersect yellow edges there or yellow edges there. And the same things for the other colors. And the even is a slight variant of the same thing. And we did this and we were happy. But now we have stronger results. Actually, these alpha k numbers are 1 over k squared asymptotically as k go to infinity. An even more surprising fact is that if you look for bipartite graphs only, since you can ask for a similar constant on what can you gain on bipartite graphs if you want to make a k-planar drawing and call this constant beta k, then this beta k is exactly 1 over k squared. No error term involved. And for small numbers, we had some kind of improvements. This is up to k equal 10. We played with it. We thought that these small problems have some interest. So what is the methodology for obtaining good k-planar drawings? So we do something similar like in the 3 over 8 theorem. So we fix a k and we want to make a k-planar drawing of a graph from a good drawing somehow. Select a number s. This will be not necessarily the same as k. S will be into how many groups randomly we distribute the underlying vertex set. Take an optimal drawing of D of the graph G, which realizes its planar crossing number, and we will be playing with this drawing. Consider now a complete graph on S vertices with a loop added at every vertex. This is what this little O means on the top, loops added, and partition this complete graph into graphs H1, H2, Hk. So every edge and every loop is in exactly one of these H graphs. And these H graphs will tell what goes to the i's plane from I equal 1 to k. So map the vertices of G randomly, uniformly, independently to the vertices of this complete graph Ks. Call types the connected components of the Hi graphs. This is what partitions these complete graphs with loops. And now define what is a type of an edge in G. Since the edge in G is mapped to 1 or 2 vertices of this Ks0, which is partitioned by these graphs, then this edge is either in a graph edge in Ks and is in one of these graphs, or the 2 vertices map to the same vertex of Ks, which means that this edge is supposed to map to a loop. But the loop is in exactly one of those things. That dictates us a type for each and every edge of G. And the following is true. The connected edges of G of the same type are not necessarily components in the graph Gi. Gi will be the graph that I map in this way to the i's plane. but this HI will contain union of components of GI. And now, following the drawing D, an edge of G in the ice plane will be drawn if the edge maps to HI, or its type is HI. So, in the 3/8 theorem, the types were the two loops and the edge in between. This is what we generalize here. And in each plane, move by translation the vertex sets that map to different types far from each other so that they do not overlap, like the yellow edges on the picture. Different components can be translated. It turns out that for unordered pairs of crossing edges, UV and WZ in the drawing D, if you define the probability that the UV and WZ edges has the same type, that it can be computed and it's independent of the choices of the two edges. So this Q thing depends on the drawing only. And if you make this drawing, that means that there is a k-planar drawing D star, such that the k-planar drawing of this D star is at most Q times CR of G. Since if you apply this randomized algorithm, then this Q is the same probability for every crossing to show up in one of the planes. So in expectation, the number of crossings is at most that much. So therefore, there exists a drawing which has no more crossings than the expectation. So I told what were the types in the earlier examples, a single edge and the two loops. And that's another example. For k equal 4, we have this design-like thing. We divide the vertices into 7 groups randomly, independently and uniformly. And then on plane 1, we draw what we see in the first column. All 6, 7 edges, 7, 5 edges, 6, 5 edges, and so on. And in this way, we listed all edges of K7 with loops. So that partition dictates the 4-planar drawing. And that actually suggests that we may have to do something with designs. And we do. And that goes back for a long time to the Kirkman schoolgirl problem, which is the first really interesting instance of this problem. So we have 15 schoolgirls, the names are from A to O, and they are supposed to walk around the school in a formation of 3 times 5 every day, and the goal is that never happens that 2 girls are in the same group of 3 twice. How long can they do it? And it's clear that not more than a week, it comes from a simple calculation, that's an upper bound, but that does not mean that you actually can construct such a thing. But here is the construction. Designs exist by construction. It was solved by Kirkman and also Cayley. And design theorists, of course, generalize this to resolve with balanced incomplete block designs. So an RBIBDSL, forget the 1, is a collection of n partitions, P1, P2, Pm, of an underlying S element set into L element subsets, such that every pair of the S element set, like the 2 schoolgirls, is contained by exactly one of the L element sets that occur in a partition class. It's a nice concept, but are there such animals out? Well, for S equals 15, L equals 3, yes, that was the schoolgirl problem. For L equal 2, this is the factorization of complete graph into perfect matchings, which is pretty close to what we did with János Pach. So, it's known that there are necessary conditions for an RBIBD to exist. L should divide S, since all points are put into a partition into L element set, so L must divide S. There is another divisibility condition that L minus 1 must divide S minus 1. You get this as you count pairs, since you know that you have a total of S choose 2 pairs of the S elements. And another way of counting gives this, which gives this divisibility relation. These two can be combined into a single congruence, as S, the total number of school children or points, should be congruent to L modulo L times L minus 1. So this condition is also sufficient for 3 or 4, and also sufficient if S is large enough. So what's the proof for this formula that this is asymptotically 1 over k squared? So we need a 1 over k squared lower bound. That was in another paper. That's the same thing. Proof for the upper bound. Fix L arbitrarily a sufficiently large k. We want to make a k-planar drawing, and set S equal k minus 1 times L minus 1 plus 1. And now there are two cases. Either you are lucky or not. If you are lucky, then an RBIBDSL1 exists. Then basically the plan is that into one plane you put all loops and nothing else, and in the other planes, every plane corresponds to a partition into L set. Put there disjoint KLs with the partition classes making the vertex set of KL. And do this thing, and if this is the case and you are lucky, then a simple calculation shows that alpha k is less or equal than this number. Well, this is close to 1 over k squared, but the other is as close as 1 as you want if you take a big enough L. And you can do that. And if you are not lucky, you still can do something. You go back to a number where you find such a design. Since there was a congruence condition, if S is big enough and not good, then you may have to go back only S minus L times L minus 1, and you find something good in between, and you can work with that. And that's equally good. You get a formula like that. So, sum on the bipartite version, which is exact. The proof for the upper bound, instead of a k as 0 to make the partition, do the following. Take the complete bipartite graph k, 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 and it's known that you can partition into k perfect matchings. So the k perfect matchings give the types that go to the k planes essentially, and it gives a 1 over k squared upper bound very easily. But the question is, can we use the lower bound? And that's a problem. That proof used a quite complicated theorem about the mid-range crossing constant from Pach, Spencer and Toth. But we don't get the same constant 1 over k squared. We don't get the same crossing constant. We still get this 1 over k squared. So I quickly say something on the mid-range crossing constant. So that amazing theorem of Pach, Spencer and Toth says, proving an older conjecture of Erbusch and Guy, who did it before the crossing lemma, that if you consider n-vertex m-edge graphs, then the minimum of crossing number of g times n squared over n cube actually converges all over a huge range to a constant kappa. And the conditions are only that the number of edges is superlinear and separated from quadratic. So that means that n is little o(n) squared and n is little o(m). That's all what we need. And that was even called a universal crossing constant, since that would be the same thing on any fixed low genus surface or anything like that. So I don't show the proof. So basically, the lower bound of 1 over k squared used that such a kappa exists, but not the value of kappa. So there was a kappa over kappa with a little disturbance with epsilon, which can be arbitrarily small, but the existence of this kappa was essential. So it turned out that the whole proof they did can be generalized, and now we have mid-range crossing constants of a large number of graph classes. We cannot tell apart any two, but very likely any pair of them are different, just we don't know enough. So if C is a graph class which is closed under the operation of taking a subgraph of a graph, splitting a vertex, so certain edges go with one copy, other edges go with the other copy. Putting together disjoint copies of the same graph, which was already in the class. And the last step is substituting vertices with independent sets, and if there was an edge between them, add the complete bipartite graph between these two sets of independent sets, and do it for all pairs. So if a graph class is closed for all these operations, then there is a kappa C universal crossing constant for this fraction if the graphs are taken from this class and these inequalities hold for the number of edges. And there are reasonable special cases of it, and that's the end. Graphs that they don't contain a K and complete subgraphs or C colorable graphs, in particular bipartite graphs, this is what we really need, or graphs which do not have an odd cycle shorter than G, and combination of these properties all fall into this category. All these graph classes have a crossing constant. Just we don't know what they are, but we believe that they are different. The reason is that we know that the ordinary crossing constant is between these two numbers, and there is a recent result which implies that the bipartite crossing number is bigger than 0.055. This is getting close to this, but still less. So that gives a hope that this bipartite crossing constant is actually bigger than the standard crossing constant. That's it. Thank you.
Any questions? Not, let's thank the speaker again.